Hello everyone and welcome to TLE Eliminators CP-31 Sheet Solutions. Today we'll be discussing the 1600 rated problem, Orac and LCM. Let's go ahead and pull up the problem. Let's open up CP-31 sheet and let's open the problem. Yeah, so basically let me just simplify the problem down. They're defining GCD and LCM, and then they're saying given a sequence A of length n, find a multiset such that it is equal to the GCD. So basically we need to find the multiset of LCM of all pair of elements and then find the GCD of this multiset. Okay, so simply we need to calculate the GCD of all LCMs of all pairs of elements in the given sequence. N goes up to 10 power 5, each element goes up to 2 times 10 power 5. Okay, so straightforward problem. Find GCD of all pairwise LCMs. Alright, pairwise LCMs. Cool. So we are given already that n is less than or equal to 10 power 5. A of I is less than or equal to 2 times 10 power 5. Right. So the expected time complexity, that's going to be around we go of n log n, we go of n log ai, etc. Like something like this it will be. Okay. All right, so let's go ahead and break this problem down. So basically we need to find the GCD of all pairwise LCMs. So this is a very like number theory-ish problem. So we'll have to take some examples and see what's happening. So for example, yeah, let's take this example 4, 10, 24, 40, 80, right? 10, 24, 40, 80. All right. So first what we're doing is basically we're taking GCD of all the pairwise LCMs, right? GCD of all the pairwise LCMs. So the pairwise LCMs are gonna be something like LCM of 10 and 24, LCM of 10 and 40, LCM of 10 and 80, LCM of 24 and 40, LCM of 24, 80, LCM of 40 and 80. Okay, and then we're going to take GCD of all of these, right? GCD of all of these, and this is the answer we need to calculate. And obviously if we had n squared time we would calculate it easily, but here we need to calculate it in the given constraint, which is like 10 power 5 type of constraints, right? Okay, now as you can see the answer over here is 40, right? The answer over here is 40, and basically if you observe, that means that whatever our answer is, let's say our answer is x, right? Here x is equal to 40. Whatever our answer is, that answer divides the LCM of all pairs of elements, right? So we just need to find the largest number which divides all pair of elements. Okay, so we have x divides LCM of a1 comma a2 for all pairs of elements, fine. So essentially what we're looking for is, let's say each element, okay, each element, let's think about each element's prime factorization. So it will be p1 to the power some m1, p2 to the power m2, so on, pn to the power mn, right? Similarly a2 is also going to be equal to something like this, right? Something like this, and each number all the way to an will have some prime factor representation, right? From fundamental theorem of arithmetic, we can prime factorize any number, right? So how do we use this to find out what can be the maximum x which divides the LCM of a1 a2, right? So basically if a number x, okay, if a number x, let's say if a number x, okay, is not basically present in either AI or AJ. Okay, if a factor x, not a number, if a factor x is not present in AI or AJ, basically x does not divide AI and x does not divide AJ. Right, if x does not divide AI, x does not divide AJ, then x will not divide LCM of AI AJ, right? So basically x will not be present in the final answer, right? X will not be present in the final answer. Right? So essentially what is happening is every factor needs to be present in either AI or it needs to be present in AJ. If it wants to be in the final answer, every factor needs to be present in either AI or AJ, right? So from this we can conclude every factor x that appears in the final answer, is either a factor of AI or a factor of AJ, or both. Okay, or both. And here let's think of factors as prime numbers. Okay, so each x will be some prime to some power. Okay, so some p1 to some power m1. Right? So let's take the given example and clarify what I mean. So 10 is equal to 2 times 5, right? 10 is equal to 2 times 5. 24 will be equal to 6 times 4, right? So that is 8 times 3. So like this. 40 will be equal to 8 times 5. And 80 will be equal to 16 times 5, right? 80 will be equal to 16 times 5. Now here, okay, let's think about what all numbers appear in our final answer. Okay, what all numbers appear in our final answer? What we can say essentially is 3 will definitely not be there, because for example, if we take a pair like this and like this, there is no factor of 3. Okay, 3 is missing in both these cases. So obviously 3 will not be in the final answer. Okay, so 3 cannot be in our answer. 3 will not be in the answer. Will not be a factor of the answer. Okay, what about 5? Well, we can see that this element has a 5, this element has a 5, and this element has a 5, right? So every pair has a 5 factor in either AI or AJ, right? Therefore 5 is going to be in the final GCD because every LCM is going to have this 5. So 5 is going to be a factor in the final GCD. Okay, what about these powers of 2, right? What about these powers of 2? 2 is obviously a factor of everything, right? But we see that 2 to the power 3, right? 2 to the power 3 is a factor of all except 1, right? All except 1. So that's why whenever we make a pair, like we take a pair of this and this, 2 to the power 3 will definitely appear, right? So we can say that 2 to the power 3 appears in all but 1, right, as a factor, right? So that also will appear in the final answer, right? So basically our final answer is going to be 2 to the power 3 times 5, because 2 to the power 3 at least has appeared in n minus 1 elements. Similarly 5 has appeared in n minus 1 elements, right? So basically the major crux observation of this problem is for some given factor, which is going to be some prime to the power m, it must appear in n minus 1 elements at least to appear in the final answer, right? Why n minus 1 elements? Because we need every pair to have this factor. If there was n minus 2 elements, then we could choose that pair and not get this factor in the final answer, right? So this is our crux observation. right? So essentially what we need to do is, right, so now we're going to think of how to solve this. So our idea will be basically, so idea, for every prime number, we keep track of how many times or what power it has appeared in each number. Okay, so for every prime number, keep track of appearance in each number. Okay, for every prime number, keep track of appearance for each number. So for example, for 2 we can say, in the above example, we have 10, 24, 40, 80, right? 10, 24, 40, 80. So these are the numbers, and let's list down the prime numbers as well. So the prime numbers will be 2, 5 and 3. Okay, so 2, 5 and 3. Okay, and what will be the counts of the primes? So in 10, 2 appears once, 5 appears once, 3 appears 0 times. In 24, 2 appears 3, 4, once, 0, 0, 0, 1, 1. Right. So here we can see that since 1 has appeared n minus 1 times, the answer will be 1, 5 to the power 1 in the answer, right? Because basically when we're taking GCD of all the LCMs, every pair is kind of correcting the whole pair, right? The pair is getting corrected. If this is missing our factor f, then this will have the factor f. So the LCM will have the factor f. So our GCD will also have the factor f, right? So it must be there in at least one of these two. The factor must be there in at least one of these two for it to appear in the final GCD. And this should happen for all pairs. So essentially this leads us to the observation that for each prime number, we're keeping track of its appearance. If it appears in at least n minus 1 elements, it will appear in the final answer. Fine. Similarly for this one, as you can see, 3 appears in this and this, right? This is simply 3 plus 1, right? This is 3 plus 1. So 2 to the power 3 has appeared in n minus 1 cases, right? N minus 1 cases. Now in this one, we can see that 3 appeared only here, and these cases do not have any 3s. So obviously if we take, let's say, this case and this case, we can remove a factor of 3, right, from our GCD. So in this table, right, from this table, we see that for each prime, take the second highest count. Okay, take the second smallest count as appearance in the final answer. Right? This is simply because, let's say we have a prime number p. Okay, prime number p, and this prime number in the first A1 it appears x1 times, and in A2 it appears x2 times, right? And in A3 it appears x3 times, right? And so on. Whenever we find the smallest x1 and x2, we find the smallest x1, smallest x2, and we take LCM, right? We take LCM. LCM will be equal to P of max x1, x2, right? That is what the LCM means. It will have the factors from both. It will be equal to this. And then this is the value which will be included in the GCD, right? So this is the value which will go into the GCD, right? So in the smallest value of x1 and x2, we're taking max of x1 and x2. So essentially, we're looking for second smallest occurrence of the prime. Okay. So in this table, we can say that for 2, if we sort them, it will be 1, 3, 3, 4. Second smallest is 3, so that is the answer for 3. For 2, so 2 to the power 3. For 3, we can say it's going to be 0, 0, 0, 1. Second smallest is 0, so 3 to the power 0. Here it's 1, 0, 1, 1, 1, 5 to the power 1, right? So the answer will be this, which is equal to 40. So essentially, our core observation that for each prime, we need to have the second smallest occurrence of that prime. Now, this can be done in many ways. You can implement it more nicely than I have, perhaps. My implementation for this I think is a bit messy, but hopefully understandable. So the idea which I used, right, my algorithm based on this idea, based on this. So what I'm going to do is I'm going to have a prime sieve. So I'll store all the primes, prime sieve to store all primes, all primes. Now from each prime, okay, I'm going to have a map basically, which will be like for each prime, right? So prime to count of that prime. Okay, so how many times the prime has appeared. So basically the two minimum counts, right? So it will be vector of int of size 2, okay, of size 2, size 2 is going to hold the smallest and the second smallest. Okay, so smallest and second smallest. Cool, right? And every time I get a new count for my prime, so for each number, factorize the number, update the minimum cost of each prime, update the minimum counts and second main counts of each prime, Finally at the very end we can set answer equals 1, and we can be like for each prime p take the second minimum, fine. That's all we need to do. And what will be the time complexity? So if you use a fast sieve, so let the maximum value of a be a and the maximum value of n be n, right? So we're going to say that the max value of a sieve can be a log a time complexity we can have. And similarly, so for the map, to creation of map does not matter. To factorize a number, right? To factorize a number, the time complexity is big O of n root a, correct, root a. But if we already have prime numbers, then what we can do is we can just check prime numbers up to this. So the prime numbers up to less than equal to x is denoted by pi of x. Okay, the prime numbers less than equal to x is denoted by pi of x. So we can say that the time complexity of this will be pi of root a. Fine. So which is basically like dividing by a log factor roughly. So this is going to be pi of root a. Now for each prime we need to take the second minimum. Time complexity for this will be simply big O of pi of a, right? So each prime we are checking. So the total time complexity for this solution, total time complexity to build the sieve is a log a. To input each number is n, and then we're going to factorize each number, so that will be done in pi of root a. So we update the second factor minimum occurrence, first factor minimum occurrence, and then the final answer will be taking pi of a to calculate, right? Pi of a to calculate. So that's about it. Yeah, memory complexity. So to store the sieve and to store the associate values of the sieve, you can say big O of a plus to store all these numbers will be n. So you could say big O of n. Each prime factor might get counted, so n log a we can say, right? We're storing each value's prime factorization. So each number can have at most log a factors, so log a prime factors, so n log a is going to be a time memory complexity, right? So this is n and this is time. Okay, so let's have a look at the code. Code is a bit messy, but hopefully it's explainable. Yeah, here's the time complexity analysis, memory complexity analysis. Here is a sieve template. Okay, so this is a fast sieve template. No issue in using this, it's just a template. Okay, you can use some smaller or like more comfortable sieve also. This is a sieve which I've been using, which I found in an old Codeforces blog. Now I'm going to have two maps. One is to count in how many elements did a particular prime appear. Second is going to be from int to vector int, which should be count the pair of primes. Okay, count whether these two primes form a pair or not. for each x, factorize x. So we're factorizing x using the primes itself, and if it's a factor, we increase the count of this particular prime. And what we can do is we can say that okay, this prime has appeared once more, and we're going to push back this count, sort, and take the first two, right? So basically what we're doing here is we're saying that for each prime number, for each prime, we just need to maintain the minimum and second minimum, right? So maintain minimum and second minimum. So we can just add it to a vector, right? We're adding it to a vector, map of into vector. We can say that okay, like we add these counts to the vector, and whichever is minimum, 2 which we keep, and the third one gets chopped off, right? So that's why we're saying we add the count, we sort it. If the size is greater than 2, we pop back, right? So we're adding it, sorting it, and popping back. That makes sure that only the smallest 2 are there in the count pair of primes for a given prime. Okay. Also, you need to keep in mind that this method will not factorize fully. What if p was exactly equal to square root of x? In that case, we have this check. If x is greater than 1, then obviously x is a prime, and we do all this stuff for x. Fine. Now, what next? If the answer is 1, yeah, so we start with the answer 1. For each prime, if this prime appeared less than n-1 times, obviously it won't be included, right? We explained that. If a prime appeared n-2 times, it will not be appearing in the final GCD. So that's why if prime is factor of n/2 or lesser numbers, then we can say that this will not be counted. So then we can just continue, right? Then we can continue. Yeah, and then basically we're going to find the count, and we're going to multiply the answer with that p, right? So for the second smallest count, right here, this logic is basically being used to find the second smallest count, right? So for second smallest count, we'll do answer times equals p times m, right? Where m is the counted p, or m is the second smallest in m1, m2, m3, so on, right? And then once this is all done, we can just finally print out the answer, right? So for basically, let's recap. We're saying that for each prime number, it needs to appear in n-1 elements to be included in the final GCD, right? So if it wants to be included in n-1 elements, basically, yeah, so basically it needs to appear n-1 times or more. If it's appearing n-1 times, we're setting it to that. We're setting it to the second smallest number, right? If it's appearing n times. So that's all for this question. For each prime, we just need to check it, right? For each prime, we need to check how many times it appeared. If it appeared enough times, we need to find the second smallest appearance count, right? Then finally, we can multiply it out and print the answer. So that's about it for this question. Yeah, we already did the time complexity analysis, so that's about it for this question. If this question was hard, I think you can brush up sieves and prime numbers and a little bit of number theory. And yeah, it was a very, like, you have to use your own logic to kind of figure out how to solve this question, right? So yeah, if you are getting stuck, do solve it, and you can rewatch the video. And this brings us to the end of the session. Thank you for watching, and see you in the next solution. Bye bye.